Okay, it seems everything is working now. Let's start with today's session. This week, we'll start with our final subjects. This is related to Chapter 11, the power analysis on alternated current signals. Then let's start with this and take care of the next exercise and examples for our final quiz or the quiz for this week. This is how our schedule looks like now. And then let's start with power analysis. What we will see here is that we will learn about different kinds of powers and how to compute them. Then the first one that we are going to start studying is the instantaneous power. For this one, what we are going to consider is that we have our two time domain signals. We have our voltage as a function of time that is going to have a phase related to voltage. Take care about this notation. This is theta sub b, the angle of the voltage signal. And for the current, we are going to have also a sinusoid that has an angle of theta sub I. This is the angle of the current. Let's remember about those terms. We were out of classes for more than 1 week. Then remember these Bm or Im are the amplitudes or the magnitudes of the voltage and current. Cosine means that this is a sinusoid. Omega t, angular frequency. The time, that is our variable here. And also our angle. Okay, then what's the definition of the instantaneous power? Here, what we are going to do is use the regular formula for the power. It means that we are going to do the product of the voltage and current. And the expression that we are going to get is something like this: Bm Im cosine of omega t plus theta b times the cosine of omega t plus theta sub I. Here, we are going to use a trigonometric identity that will help us to transform this product into a more simple equation. And when we do that, we got the following expression. Now we are going to have half that comes from the identity Bm cosine of the difference within the angles. Take care of this, is always the angle of the voltage minus the angle of the current plus 1/2 Bm cosine of 2 omega t and the addition of all the other angles for voltage and currents. Let's see here in MATLAB how this looks. I will need to stop sharing this one. And now share this one. Okay, now we are looking at MATLAB. And in this example, what I want to illustrate is how it looks like in terms of the time domain signals. We have our amplitude here for voltage, an angle for the voltage, 45 degrees, same for the current, 3 amps, an angle of 115. And when we plot that signal, this is what we are going to get. We can see a voltage signal, a current signals, and they both have a different angle for the phase. Then, if we compute the instantaneous power, check out the formula here. We are going just to multiply the voltage as a function of time and the current as a function of time. This is what we get. Look at here in blue, voltage, in red, our current, and check out how, according to the equation that it says 2 times omega, now the angular frequency of the power is 2 times the original angular frequency of our voltage and current. We can check that from here. If we check this point when the voltage is at the maximum value, we have 1 and 2 cycles of our power signal. Then what's the problem when we are working with this equation of power as an instantaneous function, or computing using the instantaneous power? Always this function depends of time. It means that in order to know the value of the power, we need to evaluate that function at different times. As an example here, I picked times of 0.5 seconds, 1.8, and 3. Those are going to be the related voltage and currents, and that's going to be the power on each one of those instants of time. That's why it is instantaneous. Then we can also plot that, and we'll see that we are only having discrete values for the power. Here, for those 2 voltage, this is the power. Look at this one, is more strange because voltage is here at the top, current is here at the bottom, and the power is at the middle, and so on for the other values. What this means at the end for us is that this power is not completely meaningful for us, because what we would like to do is to have a value of the power that we can work with and that we can explain to the user, okay, you are using all this power, or this circuit is consuming that power, then we will need a different measure to work with. Here again is that the representation of that power. Then let's see what the solution is for this issue of having used power at a specific moment in time. Then what was defined to work with alternated current signals is to work with something called the average power. In the average power, what we are going to consider is what's the amount of power into the one period of the signal, because we know that those alternating current signals are periodic. It repeats across time. We can see here we have one cycle, another cycle, and so on, and that repeats. It will be more meaningful for us to get, okay, how much is the average power that a load or a device, a circuit, is consuming during that period of time. Then we are going to perform this integral. This is how that integral looks like, and we'll see that we have 2 terms. This first term is Bm Im cosine. This angle is a number. That other angle is a number. It means that all this number is going to be just a constant that we can take out from that integral. And here, what we are doing is the integral of a sinusoid. And remember, the integral is just the addition of the entire area under the curve. And because a sinusoid has the same area at the positive semicycle that at the negative semicycle, this part of the integral is going to be equal to 0. And what we are going to get at the end is just the first part of the expression. 1/2 of Bm Im cosine of the difference within the 2 angles. First, the angle of the voltage minus the angle of the current. And you can see that that average power is expressed here as this shift of the signal up. 1/2 of Bm Am cosine of theta b minus theta I, that's the value of the average power. Are there questions until now? Okay, use more definitions. Now we are working with something called average power. Then let's see what happened with that power with our circuit elements. The first case that we are going to consider is when the angle of the voltage and the angle of the current are equal. In which kind of electric component this happen? We have three basic components: capacitors, inductors, and resistors. In which one of them the current and voltage have the same angle? Who remembers that? Please use the chat or turn on your microphone. Yes, William, thank you. This happens only on resistors. Then it means that always for resistors, the power is going to be equal to Bm Im over 2 cosine of, because the angles are the same, the difference is going to be 0 degrees. Cosine of 0 is equal to 1. It means that this is going to be just Bm Im over 2. All right. We can also use Ohm's law. We know that voltage is equal to current times R. Then we can replace this expression for Im squared times R over 2. Or we can also use the equivalent with voltage. And we know that this is going to be current is voltage over resistance. Then this is going to be Bm squared. Oh, sorry, William. I couldn't understand you. What's your question? Okay, probably it was an open microphone. And remember here what Bm and Em stands for. Remember that Em is the magnitude of our current phasor, and same for Bm is the magnitude of our voltage phasor. This is magnitude. Then it is almost the same that happened with DC circuits, but now it is divided by 2. What happened with inductors and capacitors? The difference in phase within the current and voltage on inductors and capacitors is of plus 90 degrees for the inductors and negative 90 degrees for the capacitors. It means that now the power, the average power on those components is going to be equal to 0. And what it means at the end for us is that from our circuit elements, the resistors are the only who absorbs power all the time. reactive loads, that's how we are going to call now L and C. They are called reactances. They don't absorb any average power. Remember that when we saw the definition of capacitors and inductors, they store some energy, but they bring back that energy to the circuit. It means that at the end, they are not really consuming any power. Let's check this quickly with this example. What is our idea here? We are going to compute the average power that is provided by that power source and also for those circuit elements. Then how this is going to work, we can see that this is an in series circuit. Then we can compute here this current flowing through the circuit. What's going to be that value? We will use Ohm's law. Current is going to be equal to the voltage of our power source over the equivalent impedance. We have used two components here. This is going to be our power supply phasor. Then let's do that. This is going to be equal to 40/40 at an angle of 45 degrees over our equivalent impedance, that is just 3 plus J. Now we need to plug those numbers or those values on our calculators. Let's see. Where's mine? Okay, let's use MATLAB. Please remember to verify all the numbers also. On your devices. Then we have here that our BS is equal. I know that you can see now, but James times degree to radian 45. Okay, let me, I will share with you my screen. Okay, this is the expression to get the voltage. Now we have our Z equivalent that is equal to 3 plus J. Let's compute the current. I is going to be BS over Z equivalent. That's in the rectangular form. We can get the magnitude as the absolute value of I, and we can get also the I angle equal to radians to degrees angle of I. And those are the numbers that we got. Let's move ahead and compute also the voltage over the resistor. Then VR is going to be equal to the current times the value of the resistor, and our resistor is of 3 ohms. This is VR. Okay, now we can go back to our slide and plug those numbers in there. Okay, then from here, our current was equal to 139.14. 139.14 at an angle of 26.56 degrees. Then we can compute the power of the source of our voltage source. Remember that because the current is getting in through the negative side, that power is going to be negative. You remember our first lessons during our first week? Then this is going to be our VS phasor times our current phasor. Then this is going to be equal to 40 and 40 at an angle of 45 degrees times the current. Oh, but we already have the formula here that we need to apply. Let's do that then. That's going to be BM. What's BM? 440 times IM, 139.14 over 2 cosine, don't forget the negative sign here, cosine of the angle of the voltage, 45 minus 26.56. That's going to be equal to negative 18 already. I have the note here of that value. 29.04 kilowatts. Please verify those numbers like I will do quickly here. Those operations. power is going to be equal to the absolute of Bs times the I magnitude times the cosine of degree to rad 45 minus the angle of I, everything divided by 2. Okay, yeah. 2904 kilowatts. And those are negative because that's the power that is going to be delivered or given by the power source. Now, let's compute what's going to be the power on our resistor. Then first, we need to compute the voltage over the resistor. Voltage over the resistor is going to be I times the value of our resistor. That's going to be 139.14 times 3 at an angle of 26.56 degrees. Then it means, as we know, that the angle is going to be the same, and we just need to multiply the magnitude of the current times 3. That's equal to 417.42 at an angle of 26.56 degree. And those are volts. Then let's use the formula to compute the power. The average power is going to be equal to Bm In and the difference in the angles. That's 40 times 139.14 cosine of 26.56 minus 26.56 and everything over 2. Okay, no, this is not the current voltage. This should be the voltage over the resistor. That is 417.42. Okay, we know that the cosine of that thing is going to be equal to 1 because it's the cosine of 0. Now, what we are going to get is the voltage times I magnitude over 2. And we'll see that we get exactly the same value as before, 29.04 kilowatts. And what this means? All power from source is absorbed by the resistor. Okay? Then, if we compute the power on this inductor, we'll see that the difference of angle within the current and the voltage is going to be 90 degrees. And because the cosine of 90 degrees is 0, the power on the inductor is going to be 0. All the power is consumed by the resistor. All right? Okay. Now, we are going to concentrate now in the maximum average power transfer. This is similar what we did with the analysis of circuits, of DC circuits. And what's the idea here? We have a linear circuit. It contains inductors, capacitors, and resistors, and its power supply is a sinusoid. It's working with alternated current. That circuit is going to provide an amount of power to a load. What could be this load? This load could be a motor, this could be a light, this could be the heater of a microwave or something in an industry. And what we want to do is to provide the maximum power from this circuit to that load. Then, as we did, what we want to do is to get the best value for that load. This is going to be our load to ensure that it's going to receive the maximum power from our circuit. Then we know that any linear circuit could be transformed into an equivalent circuit that is going to contain a voltage and an impedance in series. And that circuit equivalent is the Thevenin equivalent circuit with a Thevenin voltage and a Thevenin impedance. That circuit is going to provide a current to that load, and all the charges, all the loads, or all the elements are going to be in series. Then we can compute that current as our V Thevenin over the addition of those two impedances. We will replace each one of those two impedances by its rectangular form. And remember that in this rectangular form, now is going to have two parts. The entire resistive part and the reactive part. One part that becomes to all the resistors and all the resistances our circuit, and one complex part that is the reaction of the inductors and capacitors to the frequency of the signal. If we continue working in this way, we'll see that we can use the standard formula for the power, and the objective in this function is to adjust the value for the load parameters. What is going to be the best RL value and JXL value that is going to provide the maximum power. Then, if you recall from calculus, how do you get the maximum of a function? You take the first derivative and you make that derivative equals to 0. And when you do that, you will get the values that will provide you the maximum into that function. That was performed here, and what we get is that the better value for our resistor, the resistance of the load, is the square root of the resistor Thevenin plus X Thevenin and X of our load square. But the second condition was that the reactive part of our load should be equal to minus the reactive part of the Thevenin circuit. Then, because we want to meet this criterion, if we replace here, this is going to be equal to 0 because XL is equal to negative X Thevenin. This is going to be 0. And at the end, the best values for my load impedance is going to be the RL equals to R Thevenin. Let's check that here. RL is going to be equal to our R Thevenin, and our impedance is going to be equal to the negative value, the reactive part, sorry, is going to be equal to the negative reactive part of the Thevenin equivalent. It means that at the end, our load optimum value is going to be to the complex conjugate of our Thevenin impedance. And the value of the power, the maximum power, is going to be the absolute value of the voltage Thevenin squared. It means the magnitude of the V Thevenin phasor over 8 times the value of R Thevenin. And remember that R Thevenin is the real part of the equivalent Thevenin impedance. Now, what will happen if we are working only with a resistive load? If the load is only resistive, it means that now our load is going to be equal to the absolute value of the Thevenin impedance and the maximum power is going to be the same formula that we were using before. Is going to be the absolute value of our A phasor squared times resistance over 2. Okay, please, I need that you review this slide and let me know if you have doubts about how this is going to work, because this is the subject of our this Thursday quiz. Again, what's the main idea? We are going to compute the value of this impedance. That impedance is called the load impedance. That load impedance is just the complex conjugate of the Thevenin impedance. Then we will need to transform any circuit that is provided into the Thevenin equivalent. With the Thevenin impedance, we are going to get the load impedance, and with the Thevenin voltage, we are going to find the maximum power. Okay, I can see any question on the chat, or let me, I will double check here. Yes, there's nothing. All right, then let's work with our first problem. Okay, what's the idea? The idea is to get the value for this load that is going to provide us the maximum power transfer from that circuit. Then, remember, the first step is to get the Thevenin's equivalent circuit. And for doing that, we need to remove the load. Then we are going to disconnect this from here and this from here. Turn off the power sources, because this is a voltage power source. Let's label things here. BS, Z1, Z2, C3, and C4. That's a voltage power source. That's going to be now a short circuit, right? Used for illustration. Here, there is our BS power source, DS Z1, Z2, C3, and C4. And now what we need to get is the Thevenin equivalent of that circuit. Then what's the connection within those components in order to compute the equivalent impedance? Get the equivalent impedance that's also equal to our Thevenin impedance. What's the connection between Z2 and Z3? Okay, put your answer in the chat, and I will have the record of who participated today. I have one participation from William. No one knows. Are you sleeping in your bed?
What was the question again?
Yes. We want to get the equivalent impedance for this circuit, right? Then we need to check what is the connection between those impedances and compute the final impedance. What's the connection between Z2 and Z3 to start getting the equivalent?
Series.
Okay, David, thank you. Series, Dylan, perfect. Yes, please. Then Z2, C3 in series. Then we are going to have our first series impedance that is going to be equal to Z2 plus C3. And we can see clearly that that's going to be 8 minus J6 ohms. What's next? How is that impedance connect with Z1? Z1 and CS1 they are in, let's see, okay, William, thank you. Yes, they are in parallel. Then, because they are in parallel, we are going to compute our first parallel impedance, and that's going to be CS1 times Z1 over CS1 plus Z1. Then that's going to be A minus J6 times Z1 is just a resistor over the addition of everything. I will add directly that 4 plus 8. That will be 12 minus J6. Then when we perform those calculations, what we are going to get is C1 is equal to 4, C2 is equal to 8, C3 equal to minus 6 times J, C4 is equal to 5 times J, then CS1 is equal to C2 plus C3, CP1 is equal to C1 times CS1 over CS1 plus C1. Okay, please verify your numbers. I got 2.9393 minus, this is 2.933 minus J 0.5333 ohms. And we finished. That's the entire equivalent impedance, so we need to do something else. What happened with C4? How is C4 connect with all these equivalent that we have here? Okay, then CP1 and C4 are in series. And because they are in series, we will compute CS2, that is going to be equal to our C Thevenin, is going to be equal to CP1 plus C4, and that's equal to 2.933 plus 4.466 ohms. All right, and that's good because when we get our Thevenin equivalent, we already got the optimum value for our load impedance. Then from here, we can say, and this is what you expect for me to write, is that ZL is going to be equal to the complex conjugate of Z Thevenin. It means that is going to be equal to 2.933. And what we do to turn this into the complex conjugate is that we just change the sign of the complex part. Here I need the J. I will add this minus J 4.466 ohms. Now we have half of the answer here. Now, we need to compute the power, but for the power, we already have our Thevenin resistance. Our Thevenin resistance is here, 2.99. Let's remember here, this one is our Thevenin resistance. This one here is our Thevenin reactance. Then let's compute the Thevenin voltage. Then from the Thevenin voltage, again, without our load, we are going to compute the voltage that is here. Then we can see from that circuit, and we have seen this case several times before, the current is going to flow into this direction. What happened with this Z4? We know that this one is ZS1. Are we going to consider C4 for computing the Thevenin voltage or not? Yes. No. Why? Let's write that thing here. No current is flowing on C4. Then, what can we use to compute the voltage Thevenin? Yes, thank you, Coy. Then, you can use voltage divider to find V Thevenin. Then our V Thevenin, remember that that is a phasor, is going to be equal. Here we have our Vs. Vs times Zs1 over Zs1 plus C1. Our Vs is just 10 volts times Zs1. Zs1 is 8 minus J6, and everything divided in the addition of all those. 4 plus 8, that will be 12 minus J6. And as a result of this operation, let's try to do that here quickly. Then V Thevenin is going to be equal to 10 times ZS1 over CS1 plus Z1. And get also the magnitude and the angle of that voltage. V Thevenin magnitude, V Thevenin angle, V Thevenin, V Thevenin. Okay, and those are the numbers that I got. Please, again, always check that you get the same numbers. 7.0 I want to write the rectangular form too, then you can check all the numbers and see if you get the same. 7.333 minus J 1.333, and that's equal to 7.4536 at an angle of negative 10.3048 degrees, and those are volts. Now we have the voltage, we have the Thevenin resistor, we just need to compute the power. Then let's get the power. It is going to be E max is going to be equal to the magnitude of the voltage Thevenin square over 8 times the Thevenin resistor. This is going to be, that magnitude is here because remember that we already have the magnitude in there. That's going to be 7 7.45 square over 8 times. And what is our Thevenin resistor? Our Thevenin resistor is here, 2.933. When we compute that power, we get, see, power is going to be equal to B Thevenin, B Thevenin magnitude square over 8 times 8 times 2.933. Okay, and what I got was, sorry, okay, what I got was 2.368 watts. Okay, please double check numbers and so on. And this is what this maximum average power transfer means. So those are the operations that we need to do. We have used 5 more minutes. Let's see if we can at least start working with a next problem. Everybody got those numbers here? You will see that the main thing or the main problem or activity for doing here is to get the Thevenin equivalent circuit. If you get the Thevenin equivalent circuit, you already got the load impedance, and with the Thevenin voltage, you will get also the maximum power. Okay. Koi said that we need to wait. Okay, please let me know. All the procedure is exact the same as we have done before. We need always remember remove the load, turn off power sources. If it is a voltage, it's going to be a short circuit. If it is a current, it's going to be an open circuit. Get the equivalent impedance. That's going to be our Thevenin impedance. And then we turn on again the power source. And without the load, we compute the Thevenin voltage.